recording. So guys, let me explain to you how this is going to roll. So guys, today what we're going to do is we're going to start the next unit, or the first unit of the year. And we'll talk a little bit more in a moment about what makes this unit weird and frankly hard. But first of all, let me just lay it out for you. Grab your books, open to chapter 3. And let me play along with you. Elise, you have a book, right? Yes. Okay. So, guys, I know that you've interacted with this book because you did the summer homework. But what I'd like to do is give you the opportunity, not because you probably just looked at the end of chapter questions. So, guys, if you turn with me then to the beginning of chapter 3, which is on page 77. Guys, do this with me, would you? Without reading the content of the chapter. Guys, allow yourself to page, kind of 10,000-foot view, but allow yourself to page through chapter 3 and get a sense not of the material, but the organization. How do the authors of this book, and by the way, guys, one of the authors, Eugene LeMay, is actually not a friend, but a person that I know. I was going to be his graduate student. Cody, I don't even think you know this. Eugene LeMay, one of the authors of this book, actually was going to hire me away from the high school to be his graduate student and get my PhD in chemistry education at the University of Nevada, Reno. And I was actually registered for classes and ready to move to Nevada. And then I met Carla and stayed to be married. So, but I was just about this guy's graduate student. He's a really good teacher and a good author. So, guys, let's do this again. Go back to page 77. Ready? So 77, first page of the chapter, big bold letters. They tell you all about what the entire chapter is going to be about. So guys, let's break this down. What is stoichiometry? Calculations. Guys, it is the math of chemical reactions. And so it goes on, it says stoichiometry, and then it defines it. Calculations of chemistry, formulas and equations. Then guys, you turn the page again. Typically what you will see is a brief paragraph or two that introduces the concept or the content of the entire chapter. And then, guys, you'll notice that quickly Eugene and his co-writers fall into a flow. What have they done for you visually to help you identify the organization of the material? What do you see? We've got headings. What makes these headings stand out? They're big, they're red, and they got numbers next to them, right? You've got 3.1. What does the 3 tell you? What does the 1 tell you? First big idea. And guys, the first big idea is chemical equations. But then, guys, you'll notice that it breaks down from there. And as this starts to break down, we've got those big ideas that are broken into smaller ideas. So just like the chapter started with an introduction, notice that 3.1 starts with an introduction. There's a little bit of a description there, but then that big idea, 3.1, gets broken down again. And what visual clues do they give us for that breakdown? Red, bold, but now no numbers, making you realize that it's an important idea, but it's a sub-idea of the bigger idea. And then as we continue on, guys, turn to page 80. You'll notice there are big blue boxes. In those big blue boxes are sample problems. Sometimes we'll solve them in class. But guys, these sample problems are intended to give you examples to refer to if you need more support. But then guys, notice at the top of page 81, you see a heading. What does it tell you that it's big in red but doesn't have a number? It's a subpoint of 3.1, but it's the next big idea. Does that make sense in your head? Then, guys, looking at the bottom of page 81, what do we see? Big in red in numbers. That tells us that it's a bigger idea in chapter 3, but it's the second big idea. As we would expect, it's got a little bit of an introduction. What do you think we're going to see when we turn the page? Another heading. And then details from there. So guys, I would propose to you, because it's the case, that these chapters are broken up like outlines. Let me show you what I'm talking about. Go back with me to page 78. If you go to page 78, you guys are all familiar with outline format, right? Roman numerals, and then capital letters, and then Arabic numbers that break down the big idea. So guys, I would propose to you that all of these chapters are structured like outlines. So you're not writing this down, but Roman numeral 1 would be chemical equations. And then underneath that, we've got a letter A. And that letter A would be balancing equations. Now guys, does the book break it down any further from there? Does balancing equations, looking with me on 78, does balancing equations get broken down any further? Not really, but that's where the details come in. And you're like, oh, okay, so balancing equations, what are the big nuggets? What are the things that I need to know about balancing equations? And what does the book do to make the important stuff stand out? Yeah, things in bold, pictures, figure numbers. Guys, also look at this. Maybe on page 78, you see that simple synthesis reaction of hydrogen and oxygen making water. You'll notice off to the right, it's denoted by an equation number, 3.1. We will sometimes use those as references. Understand that equations are often referenced by numbers that are off to the right. Okay, so then guys, turning over again, looking then at page 80, more details about balancing equations. Then guys, we get to page 81. How do I know that this is the next idea under the topic? Because it's in red, right? And it's indicating the states of reactants. So indicating the states of reactants, and then there's more information under that. And then guys, I get to 3.2 at the bottom of page 81. How does that, where it says some simple patterns, how does that fit into our structure here? Is it a number? Is it a letter? Is it a Roman numeral? It's a Roman numeral, so that would be 3.2, that would be Roman numeral 2, and that would be some simple patterns of reactivity, and it goes on from there. So guys, do you see now the way this book is structured? Why does it matter? And the answer is this. Guys, when you approach scientific textbooks, and this is going to be one of the things that makes college ridiculously challenging, is that there is a full expectation that you learn to learn from books. And guys, I would propose to you that you've never had that experience in high school. High school teachers tend to be educators first and mathematicians and scientists second. And we pride ourselves in teaching. Guys, at the university setting, you got to understand, your professors are researchers first and teachers second, and they don't hesitate to throw a book at you and tell you good luck. So guys, you need to learn from scientific texts. And one of the first things you need to do is figure out the way the book is organized. And our book is organized as an outline. Do you understand the structure? Okay. So guys, with that said, turn to page, chapter 4, page 114. Guys, the first unit that we're going to do is actually both chapters 3 and 4. So reading the title of chapter 4, where is all the chemistry from chapter 4 going to take place? In water. It's all aqueous chemistry. So guys, what you're going to see in chapter 4, and you don't need to look, but let me foreshadow this for you a little bit. Guys, what you're going to see is chapter 4 is sort of like a sampler platter. It really is the chemistry that takes place in water. But what you're going to see is in chapter 4, you're going to learn just enough of water-based chemistry that we can talk about it for the rest of the year. But it actually defines two of the biggest units that we're going to do this year. You don't need to look, but one of the types of aqueous chemistry that it mentions is acid and base chemistry. We're going to spend a month and a half on it in January, February. We're going to spend a day on it in a couple days, but then we're going to spend a month and a half on it later. Then, guys, you're going to see the last type of aqueous chemistry that the chapter 4 mentions is electrochemistry. We're going to sample it a little bit now. When we get back to it and spend 3 weeks on it later, it's the last unit of the year, and we're going to be done, and it's going to be spring break. Crazy, right? So, guys, chapter 3 is all about stoichiometry. Chapter 4 is all about aqueous chemistry. This is going to be the first unit. You get the idea? Okay. So guys, you've never done an AP chemistry day with me before. So let me just tell you, go back to chapter 3 in your book with me. You guys understand you always bring your books to class, right? Okay. Guys, what we are about to do, we will never do again. We are going to cover chapter 3 right now. We're going to do the entire chapter in one day. And not only are we going to do the entire chapter in one day, we are going to march through this chapter one page at a time. And we are literally going to let the chapter drive this entire day. And I promise you, we will never do this again. I promise, just trust me, we'll never do this again. So guys, going back to page 77, let me ask you a question. Why would it be appropriate to just march through chapter 3 one page at a time as a class? Why would that be appropriate? Page through the chapter and see if you're not sure. Why would it be appropriate to just march through chapter 3 in a day? Yeah. You've done all of this before. Guys, all of this is a review with 2 exceptions, and I'll pause this when we need to. Guys, all of this is review. Formula masses, percent yields. I don't even remember what's in there. We'll see as we go. Guys, we've done all of this before. This is all review. Now, guys, this is where we're going to get frustrated because your success in the first part of this unit is not going to be based on your ability to learn chemistry from last year. And Sophie learned this in Germany. Cody learned this at Timpanogos. Some of you learned this from Call and me. But guys, there are different experiences in the room. There are different levels of comfort with all of this material. So please, if you get into chapter 3 and into chapter 4, because it's review as well, mostly. Guys, if you get into the middle of this and you find yourself feeling lost and confused, make me a promise. Don't look around the room. Because our first instinct when we start getting confused is we look up and we look at people around us. And then we start thinking, oh crap, I'm the only person in this room that doesn't understand what's going on. And guys, that's not true. They're just better at faking it than you are. You guys are all lost and confused. And we're going to step through this slowly, and we're going to ask and answer as many questions as you would like. And guys, over the next couple weeks, the juices are going to start to flow, and this gets better. But please do not walk out of this room today and go to the counselor and drop the class because you're like, crap, I don't know what's going on and everybody else does, and this is just not the place for me. Do you promise? Guys, this is a process, and please understand, we're developing skills and abilities, and it's not just about chemistry, it's about thinking and problem solving and all of these other things. And guys, you are going to be doing things in a couple months that you're incapable of right now. Academically and mentally, you're going to be so much stronger in a couple months than even you are now. So guys, allow yourselves to struggle and be weak right now, because we're all getting strong together. You know what I'm saying? It's kind of like me in CrossFit. I'm getting my trash kicked like every single day. Like I'm so afraid of the workout today, I'm not even gonna go. It's terrifying. It's like, but I know that if I keep going, I'm gonna get stronger, and someday I will be stronger than the 70-year-old woman that's lifting weights next to me. It'll come someday. So guys, seriously. So guys, here's what we're gonna do. We're gonna go through this slow. We're gonna ask questions. Please slow me down if you need. But guys, oh, that's general chemistry. Guys, please slow me down if you need. But here we go. So guys, grab something you can take notes on and let's get started. So stoichiometry, chapter 3. Where did my notes go? Oh, they're under my book. Okay. So guys, and you really literally can play along at home if you just flip through the chapters. Flip through the chapter. So guys, when you turn the page to, is it 70 what? 78? 78. So guys, when you turn the page to 78, we run into this idea. Balancing chemical in chapter 3. So guys, remember when you learned this last year, and this is going to be free conversation, write down things if you need. Guys, fundamentally, why do we balance chemical equations? Why is it important that we balance chemical equations? It tells us how many atoms are involved, but involved going in and coming out. What do we call the ones that go in? Reactants. The ones that come out are? Why do they have to be the same? Law of conservation of mass. Guys, we balance chemical equations because if we don't, we're violating the law of conservation of mass. So you remember this process of balancing chemical equations. It's all about coefficients. Remember, when you do it, you don't rewrite chemical formulas. So for example, if you've got the synthesis reaction of hydrogen and oxygen producing water, in order to balance this chemical equation, you can't just come along and huck a 2 right there. Why not? It's a different compound. That's actually hydrogen peroxide. But guys, when we balance chemical equations, we don't change formulas. What do we change? Coefficients. So to balance this, instead of doing that, and I know this is a simple example, instead of doing that, we need to respect the 2 oxygens, which places a 2 there and a 2 there. Is that starting to come back to you a little bit? So guys, let me ask you, do we need to do a deeper dive on balancing chemical equations, or do you just need space and time and homework to practice a little bit? Is there anything more there you want to talk about? Do you remember the hints that I gave you last year on how to, some of those things that make balancing chemical equations easier? Do oxygen last? Do you remember that? Because oxygen's sprinkled all over the place and it's so much easier to do it last. Do you want to go over the hints? Would that be helpful? Okay, so guys, hint number 1 was this, and I'm going to sort of chicken scratch. So guys, remember when we talked about the idea of balancing polyatomics intact when you can? So if nitrate is going in and nitrate is coming out, rather than balance nitrogen and oxygen, balance nitrate because it's easier. You remember that? Guys, another thing that we talked about was the idea of what we called an odd-even conflict. That you get to the point where you've almost got the stupid thing balanced and you've got an odd number of one particular atom on one side and an even number on the other side. And of course you remember how to resolve that. Double the odd number and then start over. And then Jason mentioned that idea of balancing oxygens last. And then guys, finally, the last one's really not a hint, it's just an idea. When all else fails, just strong arm the thing. Put a 1 in front of the first substance and see if that'll make it balance without changing the 1. If it works, great. If it doesn't, erase everything and put a 2 and just start over. Eventually, they'll balance pretty quickly. Guys, the other thing to keep in mind is always use pencil. Just get used to using pencil in this class. Don't write in pen. So, are we okay on balancing equations? Does that sit okay? Okay, so that's all we're going to do about that. So, guys, the second thing is patterns of reactivity. You'll notice that this is over on page 81. The question is, what on earth does that mean? We never talked last year about patterns of reactivity. So guys, allow yourself to page through the chapter and remind yourself, what are they talking about when they say patterns of reactivity? What do we got? What do they mean when they say that, looking at 82 and 83? It's reaction types. Now guys, this is where we run into an interesting little point, and you got to get used to this in AP. You'll notice that the very top of page 82, it says combination and decomposition reactions. And if you look through that section, you'll notice that those are familiar to you. But last year, we didn't call it a combination reaction. What did we call it? Synthesis. So guys, one of the things that you're going to find is that in the AP context, there are different words that we can use to refer to things that we've already learned. Like combination, our AP book calls synthesis. Still decomposition, but they use combination instead of synthesis. And we just need to learn to be flexible. So guys, when it says patterns of reactivity, what we're talking about here is reaction types. Now guys, last year in Gen Chem, you learned 5 different types of reactions. Do you remember them, or should we jot them down? Synthesis, decomposition, those are opposites. So synthesis and decomposition. Single, good. Single and double displacement and combustion. Okay. Combustion. So guys, let's talk briefly about each one of these. So what is it that makes a synthesis reaction unique? Two or more things together, but what makes it unique? If you're putting them together, what do you get? One product. So guys, this is one product. What about decomposition? One reactant. Those are opposites of each other. Interestingly, guys, decomposition reactions are always endothermic. Why would a decomposition reaction have to be endothermic? You got to add energy to something to break it apart. Synthesis reactions are exothermic because putting things together tends to release energy. What's that? Is that an always or a usually? That's a usually. You're going to find out in chapter 5, there are actually some decomposition reactions that are exothermic and vice versa. But as a general thought, that tends to be true. Then guys, single and double displacement reactions, remember these are the tradings of partners. And you're balancing charges as you predict products. Now guys, do you remember combustion? What goes in? Hydrocarbons and oxygen, and what always comes out? Carbon dioxide and water. So guys, this one is going to be worth writing down because we need a change. If you can write down that much with me right now. So this hasn't changed. Combustion always involves oxygen. Combustion always produces carbon dioxide and water. Here's the difference that we need to talk about. Guys, we said this. Last year we said combustion reactions always involve a hydrocarbon and oxygen, some carbon-hydrogen compound. It turns out that that definition is a little too constrained. This can also include hydrocarbons with oxygens already in them. Alcohols are a great example. We'll talk more about this later. But alcohols also burn, and that is technically a combustion reaction, although alcohol is technically not a hydrocarbon because it does contain oxygen to begin with. So you need to expand your understanding a little bit and understand that that counts too. Does this feel like you're drinking from a fire hose? You guys okay? Okay. So guys, we've got 2 done. Anything else there that you want to talk about reaction types? Yeah. Yeah. That's a really interesting question. Guys, the question on the table is, does it need outside oxygen in order to combust? And the answer is yes. That when alcohols, let's just use an example. When alcohol burns, it still needs that external oxygen source in order to combust. Understand that there are other oxygen-containing compounds that can burn with the oxygen they already contain. That's why you can shoot guns underwater. It turns out that inside the shell of a gun, there's actually gunpowder, and those molecules that make up the gunpowder contain oxygen. And that oxygen is tied up inside of those molecules, but it can actually be released and then reconsumed as the oxygen needed for burning. And so that's why you can shoot guns underwater and in space. But you can't burn alcohol underwater because that needs an external oxygen source. Yeah, pretty cool. You guys good? We good? Okay, so we've got 2 done. Patterns of reactivity, and we've got the other. And guys, you'll notice that we actually extended their list a little bit. We covered combustion, synthesis, and decomposition, but we also included single and double displacement, which you'll see in chapter 3 is later on, but we talked about it here. We good on that? Okay, so guys, number 3, atomic weight. Here we go. What page is this on? There we go, formula weights. So guys, looking at page 84. Give it a skim, remind yourself about the stuff. Is it coming back to you? So guys, when we talk about formula weights, when we talk about molecular weights, understand that we use those terms interchangeably, but let's remind ourselves really quickly, and I think you'll remember this, but if you want to scratch it down, you can. So guys, sometimes we'll talk about formula masses, sometimes we'll talk about molecular masses. So guys, let's start on the right. Ready? What is a molecular mass? The mass of a molecule. But guys, the trick is molecules are always covalently bonded. So it would be incorrect to say what is the molecular mass of table salt. Why doesn't that work? It's not a molecule, it's a salt. So how do we talk about the mass of table salt if we can't call it a molecular mass? And the answer is we call it a formula mass. So for the things that are ionic, we tend to call those formula masses. But fundamentally, they're the same thing, yeah. That's the thing that's interesting, is this umbrella does go in this direction. So you can use the term formula mass to generically mean a molecule or a salt, but you can't call the mass of a salt molecular. But yeah, formula mass covers them all. Yeah. Guys, is that okay? I know it's a little semantics, but something to keep in mind. But then the other thing is this, guys. You'll notice that on, does it get into them yet? Not yet. You'll notice, guys, for these formula masses, and we may as well talk about it now because Avogadro's number is the next subunit. So let's talk about it now. Guys, on page 85, what are the units that they're calculating these masses in? AMUs, which is the mass of what? Proton or a neutron. So let's just use the example on page 85. So we've got H2SO4, which is what? Sulfuric acid, one of the 7 strong ones. And guys, its mass is 98.1 AMUs. Guys, how much sulfuric acid has a mass of 98.1 AMUs? One what? Molecule. 2 hydrogens, a sulfur, 4 oxygens. That weighs 98.1 AMUs. But now, guys, what about this? How much sulfuric acid weighs 98.1 grams? A mole, right? Do you remember? So this is 1 molecule, 1 mole of H2SO4 weighs 98.1 grams. That's the magic of the mole, is if you know the mass of one thing in AMUs, you know the mass of a mole of those things in grams. And just as a refresher, remember that a mole is just a counting group, which is 602 septillion things. Do you guys remember that day that you learned about the mole? Was it weirdly interesting? It's one of my favorite days in class. It still makes me giggle. It's just so cool. Okay, so guys, are we okay on atomic weights? Are we good? Hey, maybe we should mention this really quickly as well, just so we're clear. Guys, why are the weights on the periodic table not whole numbers? They're the average of the isotopes, and how are the isotopes different? Different numbers of neutrons. Okay, good. Okay, that wasn't directly covered in this part of the chapter, but it seemed worth mentioning. Okay, so guys, anything else there you want to explore? You guys doing okay? Oh, yeah. Oh, let's take a look. So guys, let's just talk about it briefly. So looking down here at percent composition, rather than try to explain it to you, because there is one of these in homework, and typically people can just muscle through it, but so looking at page 85, you brought it up, so let's solve one. So guys, percent composition. For example, this. Take table salt. What percent of table salt is sodium? The answer is not 50%. The reason is this. When we do percent compositions, they're by mass. Okay? So the thought behind it goes like this. So sodium is 23, chlorine is 35.5, for a total of 58.5, and it doesn't matter if that's AMUs or grams because the ratios are the same. So in order to find out what percent of salt is sodium, it's simply this. Percent composition would be 23.0, we'll just go AMUs, divided by 58.5 AMUs. You got it? So when we talk about percent compositions, we're going to do them by mass. And I'm pretty sure you'll see one of those in homework. Is that okay? Is that sufficient? Okay. Yeah, the solution sort of answers the question. Okay, are we good there? All right. So guys, the next thing on the hit parade, the mole. We reviewed it already sufficiently. We are actually, you're going to see, to wrap up the day today, we're actually going to solve a large question, a multi-step problem, which will give you the opportunity to come back to some of these moles conversions. Hopefully it's a little bit familiar in your brain just from doing the summer homework, but it is the next thing in the unit, but we're going to come back to it later. So guys, the next thing after that are empirical formulas. This is worth writing down. So remember when you learned empirical formulas last year? If you don't, let me refresh your memory. You don't need to write this down. Guys, these were examples that we gave you last year when we taught you about empirical formulas. What are both of these compounds? Well, sugars. Yeah, it's awesome if you can name them specifically. In this class, you don't need to. But guys, they're both sugars. Oh! Ta-da! No, that's a 2. Sorry. There we go. Better. So guys, do you remember when we showed you these examples and then we talked about empirical formulas? What's the empirical formula for both of these? CH2O. It's a reduced ratio. Don't write that down. It's a reduced ratio, right? So this is 1 to 2 to 1. This is 1 to 2 to 1. We found out that the empirical formula for all the sugars is CH2O, which is magically why we call sugars carbohydrates, right? Remember, carbo, water is hydrate. All sugars' chemical formulas can be simplified to carbon and water. Carbohydrate, do you not remember that? Go ahead.
The sugars are having like the same elements as like alcohol.
Yeah.
I mean, they can be
Oh yeah, sugars burn like crazy. I mean, that's where we get our energy from. I don't know if you know this or not, but I mean, you grab a Snickers bar and it says 250 calories, right? And that's not just from sugar, it's fats and other things. But literally, the way that they figure out the amount of energy that's in a candy or any food, they actually dry it out and then light it on fire. And they really do. They do it in what's called a bomb calorimeter. And so what they do is they take that powder, that Snickers bar powder, and they put it in a sealed container and pressurize it with oxygen, and then they drop it into a vat of water. And by knowing the mass of the water, when they ignite the Snickers bar, the sugars and fats burn, and they radiate energy into the water. And by knowing how much the temperature of the water goes up, they can work backwards. And we'll do this in lab. They work backwards and figure out how many calories are in the Snickers bar. And it's all through combustion. So yeah, it's actually interesting if you look at it, but the metabolic reactions that take place in our body as our body takes Snickers bars and burns them for fuel is very similar to simple combustion reactions. It's way more complicated than that metabolically, but functionally it's a very similar process. It's kind of like we've got this little fire burning inside of us. Yeah, it's kind of cool. So yeah, anyhow. So guys, remember empirical formulas? Here's the problem. In your brains, you're now thinking that empirical formula means simplest formula. And that is actually not what it means. I need to expand your understanding of empirical, and this is worth writing down. Guys, the word empirical means based on experimentation. That's actually what the word empirical means. It means based on experimentation. So then the question is, why do we call simplest formulas empirical formulas? And let me explain it to you. Don't write this down, but this is the idea. Imagine if we took these sugars and we wanted to figure out their empirical formulas. How do we do it? And the answer is through well, you don't need to know the name. I want to. Here's what they do. They literally take these compounds like sugars and they rip them apart and then they pass them through a series of vessels that are called scrubbers. And these scrubbers contain compounds that selectively trap different elements. So you take a sugar and you're like, okay, I know this is made of carbon, hydrogen, and oxygen. You rip it apart by superheating it, and then you pass it through a series of scrubbers. And when you do, all the carbon gets stuck in here, all the hydrogen gets stuck in there, and all the oxygen gets stuck in there. there. And by knowing how much the mass of these scrubbers went up, you can figure out the relative amounts of the substances in the original compound. That makes sense? Well, guess what? It doesn't matter what sugar you pass through this scrubber, the relative rise in mass of each of those scrubbers is going to be the same, because their empirical formulas are the same. For every one of these, you're going to get 2 of those and 1 of these. And it doesn't matter if it's 6, 12, and 6, or 11, 22, and 11. They're all going to go up relatively the same. Therefore, their empirical formulas are the same. But we find these out through experimentation. So empirical just means experimentation. And this is the experiment that leads us to those simple formulas. See the difference? Okay, all right. So with this then, guys, you need to remember how to calculate empirical formulas. So guys, they tell us the relative amounts. And guys, this is how you calculate these things. And we'll play with one together in just a second. Do you remember this? That you assume that you've got a 100-gram sample if you're given percentages. You convert those to moles, and then you divide by the smallest number of moles to get that whole number ratio. You okay? So guys, I suspect that this math is simple enough that you can probably step through it, but I would like to solve one of these with you because we're about to get to a concept that we haven't talked about before, and I need to show you how to do this, partially because it's a lab that we're going to do in a couple weeks, and you need to know this process. So guys, here's what we're going to do, and I'm not going to give you time to do it on your own. We'll do it together. You don't even need to write down the question, but we'll solve it together. So guys, it says this: ethylene glycol. Do any of you know what that is? It's actually antifreeze. It's the stuff that's in antifreeze. So ethylene glycol is 38% carbon, 9% hydrogen, 51% oxygen. What's its empirical formula? Guys, down in your notes, let's solve this together. So here's how this goes. Was it 38.7? So 38.7, I need the numbers, 38.7 grams of carbon, and, oh, I'm writing with my paper. And guys, I would encourage you to write this down with me because we're going to play with this in a minute. 9.7 grams of hydrogen, and then finally 51.6 grams of oxygen. Okay, so guys, the first thing we need to do is we need to convert those to moles. So this is 12.0 grams is 1 mole. This is 1.0 grams is 1 mole. And this is 16.0 grams is 1 mole. And now we need to do the math. So 3.23. Hey, I can divide by 1. And then, is that 51.6? I lost the decimal. And, oh, what a coincidence, 3.23. So guys, now we know the relative ratio of these atoms in the empirical formula, but we can't write the formula yet because what do we have to do next? Divide by the smallest number, which is 3.23. So this is 1. This divided by 3.23 is functionally 3. And this divided by 3.23 is 1. So then the empirical formula would be this. Is that coming back to you a little bit? Okay. So guys, a couple interesting points. First of all, this is antifreeze, right? But look at the empirical formula. What does it look like? Sugar. And guys, the thing that's really interesting is for some of these compounds, our body cannot differentiate this from sugar, and this stuff actually tastes sweet. The problem is that it's also poisonous. Guys, dogs by the hundreds and thousands die every year because they get out in the garage and somebody spilled antifreeze and the dog laps it up like sugar water, but it's not sugar. It's actually poisonous and they die. Interestingly, the antidote, this is weird, is beer. Alcohol, it is. Actually, alcohol is a competitive inhibitor to ethylene glycol poisoning. And if you quickly drink a beer, it might save your life. Anyway, so, or your dog's life. Try it at your own expense. But it is actually a competitive inhibitor for that poison. Okay, but guys, here's the other thing we need to talk about. Is this ethylene glycol? Maybe. It could be ethylene glycol, but what do we know for sure about ethylene glycol? It's got a 1 to 3 to 1 ratio. So now, and you're going to do this in lab in a month and a half, we're going to figure out what ethylene glycol actually is. I'll tell you right now, it's not this. But guys, the question is, what information do we need to know in order to know what ethylene glycol is? What we need to do is calculate what's called a molecular formula. Write this down. This is new. This is the process of collecting or calculating what are called molecular formulas. So guys, a molecular formula is the formula of a compound as it actually exists. Now, the next bullet you don't need to write down, it's conversational. Guys, we can actually figure out molecular formulas from empirical formulas. The question is how? And guys, what we need to know is the molecular weight. So let me give you the steps. Guys, these are the steps, and this may be the part worth writing down. These are the steps for figuring out a molecular formula from an empirical formula. And it's actually really cool the way we do this in lab. You're going to like it. It's pretty tricky. Okay, let me tell you. How are we going to figure out the molecular weight of a compound? Dissolve it in a solvent and see how much the freezing point goes up. It's brilliant. And a little bit stinky. You'll see. You guys okay? Okay. How about now? You're good? Okay. So, guys, this is the second step to this process. It reads like this. Don't write it down, but just play along at home. It says, what is the molecular formula of ethylene glycol if its molecular mass is 62.1 grams per mole? So again, how on earth could we figure out the formula mass of ethylene glycol? And the answer is dissolve it in water. Water freezes at 0 Celsius. Adding ethylene glycol to water, what does that do to the freezing point? Does it go up or down? Down. That's why we call it antifreeze. Huh? The idea is dissolving the ethylene glycol in water makes the freezing point go down, meaning that you can leave your car outside on colder days without freezing and cracking the engine block of your car. It's antifreeze. So if we could take a known amount of ethylene glycol, dissolve it in water, and measure the new freezing point, we could work backwards and figure out the mass of the ethylene glycol. Well, by doing that, we find out that it's 62.1 grams per mole. The question then becomes, what is the molecular formula for ethylene glycol? Here's how to do it using those steps. The first thing we need, and you can write this down with me, the first thing we need is the empirical formula. Isn't that it? CH3O, okay. Now guys, what we've got to do is we have got to calculate what we call the empirical mass. So this is 12, 3, and 16, 31. Oh, good. So this is 31.0 grams per mole. From that information, we can now figure out the actual formula of ethylene glycol. And guys, this is not an accepted equation. We'll talk more about the equation sheets in a minute. Because this is not an equation you'll be given on the AP test. They consider this to be logical. So you'll never be asked to write this equation down. Understand the logic. But it goes like this. We can create a multiplier by dividing the formula mass by the empirical mass. So guys, the formula mass for ethylene glycol is 62.1 grams per mole. The empirical mass is 32.1 grams per mole. Guys, let me pause for a second when you're done writing. Why do I have a scooter in my room? So, guys, did you notice that I wrote these units differently? But do you know that they're the same? What does a negative exponent mean? In the denominator. So guys, the units for molar mass are grams per mole, grams divided by moles. What you'll see is that many times it's represented like this, where the -1 just means in the denominator. Get used to that. In any case, when we do this math, what do we get? 2. So what does that mean? Well, it means that the molecular mass is formula. The molecular formula is twice the empirical formula. So all we got to do is take this and double it, and we get C2H6O2, and that is antifreeze. How y'all doing? You know, the thing that was really interesting, and this was a huge scandal, is it was probably 15 years ago now, there were a bunch of French winemakers that got caught tainting their wines with ethylene glycol to make them sweeter, and people were getting sick. And yeah, it was a scandal in France because, well, it's cheaper than using grapes. Yeah, and I mean, winemaking is such an art, and they were getting to the point where their wines weren't quite sweet enough, and so instead of changing what they were fermenting, they just added antifreeze. And yeah, people were getting sick, or at least hungover. You guys good? Questions there? Okay, guys, let's plow on. What you're going to see is that, with one exception, well, you'll see. We're going to move forward, and then we're going to pause and do one more big thing. So, guys, the next thing that we run into, 3.6, where's it at? Okay. So, guys, 3.6 is this section of this chapter that talks about what we call quantitative information in chemical in stoichiometry. These are mass problems. Rather than talk now about mass problems, we're going to table this. Bless you. We're going to table this and come back to it in a minute. Because, guys, we can take this idea of mass problems and we can push it out into a bigger context. But to do that, the next thing we need to talk about, 3.7, is limiting reactants. So guys, I know that the vast majority of you already understand this, but let's be clear just to make sure we understand. Guys, what is the limiting reactant? The one that we run out of first, right? And the most visual way I know of representing this is looking at this combustion reaction. And actually, this is a combustion reaction. Paper is made of cellulose. Cellulose does contain carbon, oxygen, and hydrogen. So this is a combustion reaction. It's the cellulose in the paper reacting with the oxygen in the air. But we know from experience eventually it goes out. What do we run out of? Cellulose. Obviously, if we ran out of the oxygen, we'd all be dead. So guys, our limiting reactant is cellulose because that's the thing that limits the extent of the reaction. Now guys, if you remember, and I'm not going to go back to it, if you remember when I taught this to you last year, we talked about the bicycle analogy. Do you remember if you started with 100 pounds of seats and frames and wheels, if you have the same mass of each, in order to figure out which one you run out of first, you first of all have got to figure out how many you have. And we did that by dividing by their weights because the frames weigh more than the seats. Then we had to figure out how many we add relative to each other because 2 wheels go into a bike. Do you remember that analogy? Okay. Guys, the same thing is true here, and the way that we make allowances for those things is through this mathematical process. So when we calculate limiting reactants, we take the masses and convert to moles. In the same way that if we have 100 pounds of bicycle frames, we need to know how much each frame weighs in order to figure out how many frames we have. Then we divide by the coefficients from the balanced equation because many times these things don't stick together one-to-one. Just like bicycles are 1 frame, 1 seat, but 2 wheels. Then guys, once we get to that point, the smallest number is the limiting reactant. Again, review. And I know that this feels like we're going fast. We're going to pause. Actually, as soon as you write down this next bit of notes, we'll be done. Well, we'll be ready to tackle our last big thing. We're almost done taking notes. Actually, we're almost done with chapter 3. So guys, the last thing is this, theoretical yield. So guys, theoretical yield, which is the next thing in the chapter, the last thing in the chapter, is the maximum amount of product that a reaction will be able to produce. It's calculated by doing a mass-mass problem. But the thing that limits the theoretical yield is the limiting reactant. Okay. Let's very, very quickly. What we're going to do to wrap up the day is you are actually going to have 12 minutes to take these last 3 ideas and bring them together into one large problem-solving process. Now again, guys, your ability to solve this problem is not as based on your ability to learn, it's based upon your ability to remember. Right? Those are different. So when I throw this thing up on the screen, most of you are going to read this and your first response is going to be, what the crap? Guys, you've got to understand that in May when you take the AP test, that's the same experience you're going to have. You read over your response of the AP test. Every single problem you read, your first response is going to be, what the crap? Your success on the AP test is going to be determined by what you do next. And guys, you've got to train yourself to not freeze. When you read that problem, you go, what the crap? The next thing you got to do is grab a pencil and start writing. Because guys, if you freeze, you're dead. You gotta move. And so you start writing down things that are easy. And what's the easiest thing you can possibly write down? Balanced equations and givens. Just start writing stuff. Don't freeze. Start writing stuff down. And then as you do, sometimes the juices will flow. But guys, if the juices don't flow today, doesn't mean you're dumb. It doesn't mean you're going to fail this class. It doesn't mean you should drop this class. It doesn't mean you have no room or place in AP Chemistry. It simply means that you learned this a long time ago and you don't remember. Give yourself some grace, okay? So guys, the question reads like this. So, balanced equation. Don't write it down yet. Just read this with me. Balanced equation. If I only gave you the left-hand side of this balanced equation, what kind of reaction does it look like? Combustion. But it's not. It's not, because our products are not carbon dioxide and water. By the way, guys, do any of you know what this is? Any of you know what that is? Guess what? Doesn't matter. Keep going. It says this. Assume that you use 25 grams of cyclohexane, and you're not going to write any of this down. This is the question, and I'll leave it on the screen. Assume that you use 25 grams of cyclohexane, 25 grams of oxygen. What is the limiting reactant? What is the theoretical yield? And if you get 33.5 grams of adipic acid back, what is your percent yield? Did I tell you? Guys, every single problem you read on pretty much every test you ever take in here, your first response is going to be, what the crap? You got to get past it. So guys, allow me to help you get past it together, and then I'm going to kick you out of the nest and let you fly a little bit. So guys, I would suggest to you that if you're solving this problem, probably the first thing that you want to do is literally, and understand that on the test you would have pen, it would be in front of you and you can start mucking this thing up. Because the first thing you got to do is figure out which is which. So notice what it says. 25 grams of cyclohexane, 25 grams of oxygen. But what do we know cyclohexane and oxygen are? Reactants. How do you know? You're using them. It doesn't say they're being produced. It says they're being used. So, guys, we know that this is oxygen. So what does that make the other guy? Process of elimination. Now at least we know the names of our adversaries. Cyclohexane and oxygen. By the way, guys, remember that lab we did last year where you built the models with the kits and you had one that was a circle? That was cyclohexane. Okay. Remember that? Okay, now guys, this. It goes on from there and it says, what is the let's talk products. It says, what is the theoretical yield of adipic acid? What does that make adipic acid, a reactant or a product? Product, right? Which one is it, the one on the left or the one on the right? It's not water. So it's got to be the adipic acid. Guys, without knowing anything about this reaction, we were just able to figure out what the four things are. Just by knowing that oxygen and water is water. Now we're getting somewhere. So then, guys, we start to pick this apart. And we say, okay, what is the limiting reactant? And, oh, we just went over that. Okay, limiting reactant, we're going to take the amounts, we're going to convert those to moles, and then we're going to divide by the coefficients, like the bicycle, right? Yeah. Let's get started. But, guys, what I would do is this. I like to start here. I like to write the masses underneath things. So guys, let's get started. Remember the three questions. Maybe I should put those up and keep them. What is the limiting reactant? Now guys, let's talk about this for a second. Once you know the limiting reactant, can't you then figure out the theoretical yield? Because what does the yield depend upon? The limiting reactant. And then once you figure out the theoretical yield, you can then come up with the percent yield. Is actual divided by theoretical times 100. Now guys, as you're working on this, a couple thoughts. First of all, you will never memorize equations in this class. That's why I gave you the equation for percent yield. That paper that I gave you at the beginning of class has all the equations on it that you need for the entire year. You'll also notice that it has a periodic table Guys, for the rest of the year, you may not use the periodic table that looks like the one on my wall. The reason, guys, is because this is the periodic table you get on the test. Oh, what did you're going to ask me a question other than that?
No, I was just
Oh.
going to say, do we get this paper on the test?
Yeah. By the way, guys, when you lose this, there's multiple copies over here. Yeah. Last year, Jessica Williams started hoarding these things, and then her ministry to the class was to share them when other people needed them. Which was kind of ironic because they weren't hers in the first place, but it made her feel loving. Okay, so guys, you've got 7 more minutes to solve this entire problem. Figure out the limiting reactant, figure out the theoretical yield, figure out the percent yield. Then, guys, we will solve this together, which will run us a little bit into pride, but we don't get to leave anyway. So we're okay. Sir? Do you remember the bicycle analogy? So we talked about the idea that if you had 100 pounds, if you have 100 pounds of frames, 100 pounds of wheels, and 100 pounds of seats, you don't know how many bikes you can build, right? Because you don't put these together, a pound of frame, a pound of seats, and 2 pounds of wheels, because they don't weigh the same. So the first thing we had to do is figure out how much does a frame weigh, how much does a seat weigh, how much does a wheel weigh, and we divide, and that tells us how many of each item we have. But then when we start bolting them together, it's not 1 wheel, 1 seat, 1 frame, it's 2 wheels. So we divide by those coefficients, 2 and 1 and 1, to get the relative amounts that stick together. And
So
that,
the remaining amount after you divide the wheels by 2 is the amount of sets that you can make.
correct, exactly. And so that same logic counts with chemicals, only instead of dealing with individual items, we're talking about moles of those items, but we still divide. By the way, guys, I'm completely comfortable with you working with the people around you if you would like. But realize there's a fine line between collaborating and riding on coattails. Make sure that you're gaining from the conversation. Yeah. Theoretical yields are in grams. Yep. So guys, we're going to go for about 2 more minutes, and then we're going to do this together. So guys, we're about 1 more minute. So guys, we're going to wrap up in about 15 seconds. If you're not done, I know how frustrating this is. You're like, I was almost there. I got to finish. I think you're going to find that you're going to benefit more from the conversation than you are from punching in those last couple numbers. Can we talk? Okay. Hey, let me mention one thing just in passing before, because there are so many things that you're seeing for the first time. Like, for example, why did they represent the hydrogens twice? Did any of you think about that? Yeah, why are the hydrogens represented twice? And here's the answer. This is an acid, right? What do acids do? Give away hydrogens. And when you write the chemical formulas for organic acids, we tend to write the acidic hydrogens either first or last. So what this is telling you is that this particular molecule has got 2 hydrogens that are ready to be released. By the way, will this molecule release these hydrogens completely? How do you know it won't? It's not one of the 7 strong acids. So it will do it partially, but not completely. Because if you're not sure what I'm talking about, remember this one that you had to memorize? Vinegar. Another reason we write the hydrogen separately, this is the acidic hydrogen. These are hydrogens that do not come off. Therefore, they're not the acidic hydrogens. Okay. With that said, here we go. So guys, I think probably, well, let's try. We have 25 grams of C6H12. We have 25 grams as just O2. So what I'm doing, oh gosh, that's bad. So what I'm doing is I'm figuring out the limiting reactant. So in order to do this, 72 and 12, 84. So this is 84 grams in 1 mole. This is O2, so that's 32 grams in 1 mole. Can you help me with the math? What's that? 0.298 moles. And then what about here? 0.781 moles. Okay, so now we know the relative numbers of moles, but we're not done because these do not stick together in a 1-to-1 ratio. It's actually 2 to 5. And from that, so this is going to be approximately 0.1 or thereabouts. This is going to be approximately 0.124. And guys, we're dealing in approximates. But here's what we know. This number is smaller, right? Isn't it? Okay. Therefore, that's our limiting reactant. Questions on part A? Part 1? Part A, whatever that is. You okay? Okay. So guys, here's what we now know. This is what we're going to run out of first. What does that then make oxygen? Excess. So we've got limited amounts of cyclohexane and excess oxygen. So now our question is, given a limited amount of this, how much adipic acid can we make? And guys, in order to solve that problem, it's a mass-mass problem. So we start with 25 grams of C6H12. What we want to know is how many grams of adipic acid can we form? So guys, this is a mass-mass problem. Remember, there's a rhythm to these. Grams to moles, moles to moles, moles to grams. So the first thing we've got to do is go grams to moles. This is something, we're going to let that go. This is something that we didn't directly talk about, but it is a skill that you learned last year. So we're going to go grams to moles. And again, guys, if you don't remember, don't freak out. Remind yourself and learn. So this is 84.0 grams is 1 mole of C6H12. Then we need to know the mole-to-mole ratio of C6H12 to C or H2 C6H8O4. And guys, that ratio is found from the balanced equation. Is it 2 to 2? And then 1 mole of this adipic acid is 2, 72, 8, and 64. 146? So 146.0 grams. Just help me with the number. What is it? So 25 divided by 84 times 146. 43.5. So guys, that is our theoretical yield. If the stars line up and if all 25 grams of that cyclohexane perfectly reacts, we're going to get out 43.5 grams of adipic acid. Third part of the problem, did we get out 43 grams of adipic acid? No, we only got 33 grams of adipic acid. We just failed that lab. But we want to know the percentage. So now, can I write down here, or is it too low? Can I try? So percent yield is actual divided by theoretical. Is the actual is 33.5. The theoretical is 43.5 times 100. What's my number? Technically, it should be 3 significant digits, but yeah. So guys, that was, that was probably what, 7 or 8 weeks of material from general chemistry last year in 78 minutes. That was a big day. So guys, thoughts or things that you want to talk about relative to any of this? We okay? Okay, so guys, this then is how the days will end. Unlike general chemistry where you got handed worksheets, here you get homework assignments out of the book. So I would encourage you to write this down. So guys, out of chapter 3, this is your homework. At the end of chapter 3, you're going to do 3, 5, 7, 14, 19, 25, 37, 45, but only part A. 49, 57, 63, 79. Now, if you don't want to write this down, guys, it's posted on our website. It's not yet, but it will be, because I always post our notes. But guys, in addition to that, there's a little bit more. So this is not due on Monday, this is due on Wednesday. We are going to summarize chapter 4. The summary that we are going to do is a simple outline. Do you now understand why I spent so much time helping you see how chapter 3 is like an outline? Do that to chapter 4. This is the only time you will outline a chapter. Guys, throughout the year, I'm going to teach you other summary strategies, but I think you're familiar with outlining, so do it. If you're not, watch the screencast because I showed you how to do it earlier in the day. Then, guys, and this part is due on Monday. On page 121, I'd like you to please look at table 4.1. This is going to be your third touch on that solubility table. Guys, remember you were to have memorized the solubility rules to apply them for the quiz. Then when we graded the quiz, we talked about some of those trends. What I'd like you to do is go back to this table on page 121 and put those trends in writing. All nitrates dissolve in water. All acetates dissolve in water. All group 1 compounds dissolve in water. All group 1 salts. That's not for us. Guys, go back to page 121 and summarize that table in a way that not only makes sense to you, but a way that will help you do better if you need to retake the quiz. So, guys, this is due on Monday. This is due on Monday. That's due on Wednesday. Yes, sir? No, thank you. I really would prefer that you not type anything in here unless there's a solid reason why you would rather. The reason is, again, because you don't type on the AP test. Okay, so, but if we want to type, let me know if we need to. Guys, we did it. That was a pant load of stuff. Do you have the energy to say the pledge?
Yeah.
Let's do it.